Hello and welcome everybody to today's webinar series of webinar with the mmWorks Inc. covering different topics. Today, our webinar is going to cover the application of what is called streamlined design of mmWave array antennas for 5G. You all know the channel that 5G is presenting nowadays. I am Adam Kibir, a sales manager. I have with me Dr. Ahmed Kibir. He's a technical manager, and together we're going to do this presentation for you today. Just some notes as a start. Please mute your microphones, and if you have any questions, write them in the chat window, and the instructor will answer them after he's done doing the technical presentation. In addition, a webinar link will be sent to all attendees via email later in a few days. Now, what is the agenda of nowadays webinar? We're going to be speaking about giving you an overview about the company, like locations, products, licenses, then move on to the technical presentation by Dr. Kibir. And after that, cover some other applications that the mmWorks provide analysis solution for, and share with you some learning resources, and share with you also how to submit your request for any further follow-up action you want to take after the webinar. So namely talking about like how to get a trial, how to get quotes, how to get the one-on-one demo, and so on. So our company was founded in the year 2000 with a head office here in Montreal, Canada. We do have also branch offices in Germany and Japan. However, we have heavy presence in North America, Europe, and Asia. So you can see pretty much we have presence worldwide. And apart from the 2 or 3 locations we have, we also work through the SolidWorks resellers worldwide. And so you can always address them to a SolidWorks reseller to know more about our products, or get info or brochures, or ask any questions. Of course, to be able to provide the best solution in the market, we have to have a strong R&D department, which we do with about 85% of our engineers are master's degrees or PhD holders. Now, to speak about our products, mmWorks offers a lot of products, and all of them cover the electromagnetic simulation. So we pretty much cover all the frequencies from DC to a few gigahertz. The main product that we put in the market is one of the main products is EMS, which covers what is called low frequency electromechanical electromagnetic application. We also have another major product called HFworks for RF and microwave, and that's what we're going to use today in carrying this webinar today about the millimeter 5G antennas. We also offer 2D, which is equivalent to EMS, except it's a 2D solution, but the EMS is full 3D, and motor wizard for customers who like to analyze motors, and it's a pretty good solution for motors. So in addition to these 4 main products, we have what is called multi-physics capabilities, because we also offer some motion, some thermal, some coupling to structure, and circuit coupling. All of that adds to the picture and make our solution or our solutions multi-physics solutions. Well, this being said, today's webinar again, we're going to use HFworks for it, the product that is fully integrated inside SolidWorks, and all of our products are integrated inside SolidWorks, are gold certified products for as far as SolidWorks. Now, let me move the screen to Dr. Kibir to show us the technical presentation. Then we'll move to sharing with you some info about our licenses and how to get help with us. Thank you for listening to me. Here you go, Mr. Kibir.
Yes, thank you, Adam. Let me sharing my screen.
Yeah, we can see your screen now.
Okay.
But we see different windows, so.
I think I need to stop this out.
Yeah,
So
yeah,
I
we
hope
got good.
everything is clear now
No,
for everybody, and thank you all for joining us today. So today I want to walk you through uh, the presentation about how we actually go about doing antenna simulation. 5G happens to be the application, but antennas in general, how we do that with our flagship product, HFworks, that Adam just spoke about. And the agenda is really very briefly kind of set the stage for this 5G, because as a technology, it's really heavily relying on antennas. So I'd like to briefly go over, the 5G context and the need for antennas. And I'll go over an example. So an example will show you how the workflow is and what kind of results you can obtain and how you can interact with them through the software. And close with a conclusion after that, and then we'll take time to answer questions. If you have any questions, please, as we go along, feel free to type them in the chat box, and we'll get to them at the end of the presentation. So the promise of 5G, I guess everybody's kind of aware that this is really where we are today. It's really a key enabler for the future of innovation in our current world, and it touches a lot of sectors and a lot of our aspects of our lives, from smart cities to smart homes, wearable technologies, connected IoT objects, and all
excuse
of that.
Excuse me, Dr. Kabir. An attendee said your voice is not clear enough. You can please raise your voice, but there's also some background noise. We don't know what it is.
Is this better?
Yeah, yeah.
Okay. So sorry about that. So
Okay.
I was saying that this is so this is actually the context, and we know that the 5G is important. At the end of the day, 5G is about wireless connectivity, and whenever you say wireless, then you talk about antennas, and then whether you're doing a single antenna or doing massive MIMO, where you have many antennas, or array antennas for beamforming, and increasingly we need to use the higher spectrum of millimeter waves. So really, the antennas are really a critical technology to 5G and beyond, even 6G and so on. So really, it can't be stressed enough. So today we're going to go over the 5G antenna design example, and the simulation process that gets us to the antenna design is going to be carried out inside HFworks. And HFworks is essentially a product that allows for 3D EM field simulation, and it is embedded inside SolidWorks for the CAD. It is gold certified by SolidWorks, and it does come with the ability also to do not just the electromagnetics, but also the electrothermal simulation. And the idea of HFworks is the embedding inside SolidWorks, that we take a full advantage of what SolidWorks offers in terms of CAD capabilities. It's a very powerful CAD platform that allows for the easy manipulation, creation, and editing of geometry, with lots of features that makes the whole workflow very, very productive. So in a bit more about HFworks, so it's essentially, we have this 3D electromagnetic simulation package. It's based on the finite element technique in the frequency domain, okay? And the workflow really is kind of straightforward if you think about it. So we start with the CAD, and that has to be created or imported or opened or edited or whatever inside SolidWorks. So that's really the front end. It's the SolidWorks front end. And HFworks sits as an add-in inside SolidWorks, so it's not a separate piece of software. It's really kind of part and parcel of SolidWorks in a way. Once we have the CAD model, then we go through a pre-processing phase, which is essentially setting up the materials and and the boundary conditions and all of that. And obviously, if there are any parametric or configuration and multiple configurations or things to be analyzed, then that is done and set at the pre-processing phase. Then we do the meshing, and we can use for people who are not experts, it's probably preferred to use adaptive meshing. For those who are actually quite knowledgeable and so on, then you can cut solution time and so on by going straight and controlling the mesh manually and getting automated mesh refinement that the software intelligently helps you to accomplish. And obviously after that, then we go through the post-processing and look at the results, the field results or the circuit parameter results or the antenna parameters, as it would be in this case. So to show this, so today we're going to consider design, okay? And the idea here is really we picked an example that illustrates a little bit a way to kind of address and streamline this design complexity and reduce fabrication costs. We picked an example. It's in the open literature, so it's a 5G 28 gigahertz resonant antenna, and it has this kind of unique feature that it can. It's a dual excitation. Dual excited. The basic element has 2 excitation ports, and then out of that you can build an array. Okay, and I'm showing here a single cell and a 2x2, but you can also go higher. And the interesting thing about this design is that you can actually do beam steering with less number of ports, and I can share with you the reference paper if you're interested. And basically, the idea is that you can use this this kind of excitation to go like from, if you go to 3x3, you can actually excite the additional element without additional ports. So that's really one of the concepts of this example that we picked. And so for this, at this point, I would like to switch over to the SolidWorks, do a live demo of what we're getting and how we simulate this, how we set it up, how we get the results. Okay. And that will be switching over to this SolidWorks. So this is a live view, obviously, of the SolidWorks interface. I have here the 2 examples. I'll switch over to the model. So this is my array, okay? And in another window, I have the single element design. Show this. For some reason, I'm showing a black screen. Adam, can you confirm that the screen is black for you?
Yes, sir, it is black.
I'm not sure why this is the case. It's hiding my model. You just. So this is. So let me end at any rate. Let's see, maybe this will help set it up. So basically, what we're looking at, this is the SolidWorks interface. And maybe I can go back to this model where we actually see the
yeah, we can see the model now.
Yeah, so this one is the 3D assembly of the array. I wanted to show the single element. So the idea is that inside SolidWorks, this is where you actually be building structure, the CAD geometry. And as I mentioned, it's quite powerful. You can do very complex structures, fully 3D, fully parametric, and so on. And here, for example, we're hiding the air, but you can see that there is an air box around this that we need to do the simulation. And this is, we are inside SolidWorks here. And once this model is ready, then this is the HFworks environment where we do the simulation. So you see the name of your assembly, and you see that HFworks has this tab which is added in. So it's really kind of part and parcel of SolidWorks. It's fully embedded in SolidWorks. And then you have this menu, and you have the, if you have more than one product of EMWorks, then you see them here. And in this case, we have the HFworks product. And if I go and open the demo library, okay, and this is where you can navigate a whole bunch of examples, okay, the kinds of things that you can do. Obviously, in the antennas, you can have, you know, many different types of antennas, and all of these are easily accessible. The geometry is ready, everything is set, and you can have them in planar, or you can have some antennas in waveguide, or some wire antennas, and so on. And then if you're going to go to S parameters, then you can also have a whole bunch of different structure that you can see, you know, what kind of models you can build and test inside the HFworks. To do, you know, some filters and all kinds of connectives and transitions and so on. And there are examples for TDR for people who are interested to do time domain reflectometry and so on. And HFworks does have also a resonance solver, so it looks for the eigenvalue solutions for different cavities, resonant cavities. And it comes also with a few examples of multiphysics, so electrothermal problems, whether for antennas or as parameter heating applications or heat loss in structures. And there are obviously some few examples where parameterization is used, like, for example, to tune a filter and so on, or to optimize the coax to waveguide cavity transition, and so on and so forth. So this is a good starting point for those who are interested to learn more about the software. You could start here and look at these examples, and there is obviously a tutorial library and so on. So this gives you an idea about the spectrum and of applications that you can do with HFworks. So now let us get back to the subject matter of today, and let me just, for the sake of, so let me just see if this model, maybe if I close this window and reopen it. So maybe now I'll be able to open recent. This one. All right, so I think that there was a. So this is actually, I want to start with the single cell model and just walk you through very quickly how do we analyze this. So you can see here that I already have two simulations. The process is really straightforward. Okay? So you go here and you say, I want to study this antenna. And you have here types of simulations you can do. You can do antenna, or parameter, time domain, or resonance analysis. So for doing antennas, and the menus, by the way, get configured according to the study type. So here there are a few options to set up for your simulation. You can set up your frequency sweep, the meshing option, adaptive, manual, and so on. You can fully control this. And if you're doing any thermocoupling, electrothermal analysis, you cannot. So I'll just go ahead and say, okay, I didn't set any frequencies or anything. So you notice here that we create this study or a simulation scenario, if you will. And at any time, if I want to edit this, I can go back and then go to the properties and play with this. So for example, if I wanted to do only look at the port simulation, the port impedances and so on, I can do this port simulation. If I wanted to do parameterization, if I wanted to save or not the 3D fields, if I'm concerned about if I want to look at fields or just interested in this parameter. And one of the other features is this power handling capability, which allows us to compare break down fields. So if you're doing a high power application, you might want to look at that. Okay. So all of these, you can edit them and change them at will. So if doing parameterization, and you see here that if I did parameterization, then the icon of parameterization will pop and will let us know that this is parameterization stack. Okay. So what we've done in this antenna, okay, is actually simulated this, and we try to optimize this transition, okay, to feed the antenna properly, and that is very sensitive to the width of this narrow microstrip line. So we did the parameterization to see, to compare different scenarios, and you see the width is here of 0.02 to 0.05 millimeters. And once that was done, we actually simulated the kind of the optimal scenario and dive deeper into the details of that simulation. Okay. So how we did this, I'm going to get back to this briefly, shortly, and how we did this. I'm going to just walk you through the process in this study, which we're not going to simulate. So by the way, if I wanted to set the frequencies and so on, you can see this is not set up at 28 or any of these things. Or I want to shortcut things, I could just drag this study onto this one. And then I inherit everything. Okay, so this study now is fully set. Okay. If I go back to these properties now, okay, you notice that my frequency setup is already now, it's a proper frequency. So it's very easy if you wanted to do a new simulation based on an old one and just adjust the parameters that you need. But if you're starting out, okay, and you wanted to set a study, then you can see the three main building blocks are material definition, boundary condition, and mesh. And as I said, you can do automated like adaptive meshing or manual meshing. And in this case, we've done manual meshing because we know exactly what to expect and where to mesh, and it saves us a bit of time in doing this simulation versus waiting for multiple adaptive passes. So the process of material application is straightforward. So you can go to the material library by apply materials. Okay, you can find the material and replace the material. You can use your favorites, and you can populate this with your favorite material that you use. Or if you've used the recent material, you find it, well, in these materials. So in this case, we're using a Rogers substrate on which we've done this. So that's about the material that I recently applied. So to apply materials, you go to this. You can part by part, or if the part has bodies, you can apply body by body. So in this case, each part has single body. Okay. So I can go here, and this is what the material library looks like. Okay. So you can search for a material by name or browse them by category. So you group them by categories. And for substrates, for example, we have the whole gamut of substrates. We have the Rogers materials here. And then if you apply material, let's say, oh, this is a Rogers material, you say, okay, now that material is applied, and you see it there. Of course, I applied it to air just to illustrate the point. Okay. But I can drag this onto this one and say, this is actually my material. So this now becomes the roid. Okay. And I can go back to this one and say, this is actually air. And it's straightforward. To see how easy it is to play with these things. The other neat feature about materials is that as we are embedded inside SolidWorks, so you can have some mechanical parts that are not relevant for simulation. And so we have this folder where you can just drag things that are not relevant. You can exclude them from simulation. Okay? So it will give you a warning and so on, but for now, for example, if I did this, then that part will not be considered in my simulation. So it's an easy way to work with true mechanical designs from your mechanical engineer and so on. So really, so the idea is materials is very straightforward. There is even a nice feature that I like to mention usually is that if you create a materials folder, if you have lots of bodies, okay, so let's say you want to have your substrate is a Rogers substrate of something, this one, and you say, I have a lot of materials, I want to apply materials. So you can just select a bunch of bodies and control select. And if you drag them into a folder, then they get applied that way. So, and you can make these folders, if you want to make them permanent, so you make this folder permanent, current study or log study type. So this is basically now, whenever I open a study, I'll have this folder because I'm always working with it. So I apply material by just putting bodies in there. So this is briefly what you can do with material. The next step is boundary conditions. So in this case, we have to define ports. And you notice here it's giving me these warnings because I took out some geometry that was, I excluded in that was in the original definition. But the port definition is really straightforward. And this is actually, I want to maybe illustrate this. So the way you define ports, you have the geometric entities and then the properties of the port. So the geometric entity is straightforward. We need ports need faces. So this is let's say like this my port 1. It has a face, and then you can here set if it's differential and then or single-ended, and then if you want to calibrate this port, completely impedance, power voltage, and so on. And you can control the number of modes of that port. So you can do multimodal S-parameter simulation. And then if you're sometimes in complex geometries, you want to see what is that port. So this illustrates to you what port it is, so you can recognize your feature. You can pin this. Okay? So if I have 5, 6 ports, whatever, I say OK to one, okay? And then say OK, and then I move on to the next one. And then I'm doing the second port. So this will be my second port, for example. So it's in one shot, you can do all of these things. So the material boundary conditions for antennas, you have all these types. You can have multiple ports, and you have symmetry, perfect electric, perfect magnetic, symmetry conditions, impedance surfaces, and obviously you need the radiation boundary, which is the outer boundary on the box. So quickly, just to illustrate the capabilities for manual meshing. So here you can see that we have some mesh control. So let me go through quickly how this works. If you want to apply a mesh control, this is where you essentially say what elements per wavelength or what actual element size you want on certain features. It could be on a body, on a volume, and this will override the default element size, which is computed based on wavelength. Or you can go on a face, or you can go on the edge. So typically in high-frequency electromagnetics, really the critical parts are the edges. So let me show you how we actually pick those edges. So if you look at this is actually quite tedious if you want to do it. So the idea is, in this case, we only really want these faces. Okay, this is the conductor face. And all we need here is really, we want really those edges. So we can right-click here and then extract the edges. You've done that in one shot. Okay. So on these edges, I want, instead of I'm doing second-order elements. So instead of going 6 elements or 0.3, I can go, let's say, do twice that, for example. Twice that. Okay. So it will update for me the average element size, and I'm more set like that. So it's actually telling me that those entities already have boundary. So they already have those mesh controls. Okay. So and when we do this, okay, and then we create the mesh, then you see that your mesh is actually following those instructions. So let me go back now and show you, for example, what that mesh looks like. Let's say mesh. You can see that without waiting for adaptation, I already got this nice transition mesh. And this is, it might be over refined in places, but that's you still save time with a single pass, and you get very accurate results. Okay. So this is very briefly how we do set up the problem and so on. So let me go back now to our first study. So I go quickly over. So we have an antenna part which is hidden. I can say show it from here as well. So that's my antenna box. Okay, my air box. Okay. So this box is dimensioned such that we have enough distance from the radiating element. So it's typically the further you go, the more precise your radiation pattern again is going to be, but you don't want to be too close, less than a half wavelength. So in this case, we took a full wavelength to get really, have no issue with the boundary itself. Then we can look at the port. So this is one port. That's the second port. And this is our radiation boundary. And then we have the perfect electroconductors inside in there. We have the mesh control that we saw. And now this is the parameterization. So in this study, we were not sure what should be the width of those transition lines. So we actually created a whole number of scenarios to parameterize. And in the parameterization, there is actually a neat, unique feature that you can use. So this is a physical dimension, PDP, physical dimension parameterization. So we can actually parameterize things in millimeters or centimeters, whatever the unit is. Okay. So we're actually, we assign two widths. We could independently vary this one and this one. So, but out of, and that gives us, two dimensions, D1 at sketch. So you can see this is referring to the entity in SolidWorks, okay? And this is the second dimension. And we vary them between 0.02 and 0.05 in steps of 0.01. So if you look at all of these, and you can parameterize other parameters as well, and then you generate the scenarios, and we have here generated essentially 17 scenarios. We picked a few of them, essentially wanted both of them to be both 0.02 and 0.03 and so on. So we have altogether 4 different scenarios that we simulate. You can also parameterize simulation variables, not just geometry. Okay. And here, so this is physical dimension, but you can also parameterize in wavelength. And this is very interesting if you're doing wideband antenna design, for example. So you want certain dimensions, especially the air box, for example. If you want it to always be lambda/2 or lambda or whatever, then you can pick this wavelength parameterization, and it will allow you to parameterize things electrically. So as frequency changes, the model dimensions will be adjusted and simulated accordingly. That's really a unique feature that this parameterization offers. Okay. So now you can see that this study, okay, is, and by the way, when you go to the meshing, and if you want to now show mesh, then you can say, okay, we have different meshes, different scenarios. Okay. They're going to look very similar because we're just changing this inner width here. So let me go back and hide the air box here. So to focus on this, and then now the difference is what you see here is that we have this parameterization. We have the results. Okay? So you can see here in this study, to get it, to get the simulation done, I was basically interested in the S parameters. So in showing this S parameter plot. Okay. And when I plotted this, so this is actually, these are my mesh parameter results. So this is my plot one. And you can see that I have actually in blue is our simulation, and in red is the measurement data that we got from the publication. So you can see that this antenna is actually, the design is pretty good, and the software is predicting quite nicely the resonance of the antenna at 28 gigahertz. So that was really the important thing to notice here. And as a matter of fact, I can actually go back here and show you that to create a 2D plot. So I want to go, I can pick from which simulation? to get, or I can get all simulations, which parameters, so you can plot as parameters or even VSWR or some other parameters there, and which S parameter in particular. So in this case, we're doing S11, and from which scenario. So I can do, okay, show me all S parameters from all scenarios, add them, and it adds them in one chart, and then you actually can see now, okay, what the different scenarios give. Okay, and we see that the scenario 16 is actually, which is 0.05 millimeter, the last one, is giving me essentially the best performance here. Okay. And this is the 2D viewer, and it has all these nice features that you can play with your graph and so on. And one of the things you can do is actually look at the data at the same time. And obviously you can move around and look at, you know, what your results are at different frequencies and so on, or actually you can go and pick in the frequency, and you can control select, and you have, so you can look at your data in different ways. With the roll of a mouse, you can zoom in and zoom out, and it's quite user-friendly to allow you to play with how you look at your data. So this is the result of our parameterization. We saw this. So this is basically telling us that this scenario 16 is the one we should be working on. So my second study here was scenario 16. Okay, so I did a full simulation. I saved the fields, and you notice that the difference now, once we save the fields, we can actually look at far field data, electric field, magnetic field, all those things. If we had losses and loss density and power loss, we can compute that as well. So let me briefly go over this one. So the configurations is really a way for us to set, if you want to de-embed so if you look at, if you want to add a de-embedding or renormalize your impedance, that would be a configuration. Okay, so by default, we're just looking at the intrinsic S parameters here. The results table is where you see your tabular data, the S parameters, the magnitude and dB, and here we've done this at 28 gigahertz of sender frequency, and you look at this, and you see that we have about 15 dB return loss. We have 27 dB isolation between the two ports. Okay. I could look at the port results, look at my gamma, my impedance, and so on. So all of this is feasible, and the data, you can export it at any time to an Excel sheet, something like that. If you want to do more with this, you can additionally, generate a table, circuit parameters table. You can just pick one parameter and put it in a table. Or for example, if you wanted to compare from different different studies, for example, different S parameters, you can, the same way we do the plots, you can do this data. If you have multiple rows, and then you can swap things around. So it's really quite easy to play with the tabular data stuff. The plots, we've just seen how to do the plot. So I was showing this plot here, which is essentially now comparing S11 and S22, and because this is symmetric, so this is really makes sense that this is they on top of each other. The structure is fully symmetric. You can plot, obviously you can go into and put this on this chart and look at the data in this chart as well. And this chart is a similar look and feel to the 2D. Okay? You can do similar things and move your cursor around and look at the data tabular, and the same kind of thing that you've seen before. So you have to do new points. And you look at, and you can again zoom in and out with the roll of the mouse very quickly, very easily. So this is basically where we look at the circuit parameters. Okay. And now to look at the antenna results, we have this antenna simulation section. And the way we do this is every time you want to do a far field calculation, we do a far field case. You can give it a name here. You pick the frequency, and you can decide what excitation you want to put. So for multi-port, for phased array antennas, array antennas in general, this is where we get to set those weights, the power and the phase of each port. Okay. So in this case, if I'm exciting both ports, okay, and this here you set the resolution for the far field calculation, in which degrees, how many degrees in theta and phi that you wanna do to complete the far field. And once you do a case, then basically it creates the results table for that case. So for example, here we kind of followed what's in the paper. We said, okay, if you're gonna do a port 1 at phase 110, so I can always, so as a definition, go back and see what we did. So port 2 at 0 phase and reference phase, and 1 is the 110 difference with respect to it. So what do we get then? Then we get this tabular data. So this is where we're looking at what is the return loss at this frequency, and then we have all these incident power, 1 watt on each port, and how much is accepted, how much is radiated, what's our gain, and so on and so forth. So you get all of that data. And then if you want to do the plots, then here is where you do the plots. So basically, if I'm looking at the far field case 1, I can look at what is this polar plot. I can look at it in 3D, obviously, zoom in and out. You can see that's my radiation pattern. I can take cuts of it in the theta and the elevation or azimuth angle. And you can see that's a correct plot. And you can do obviously the electric field. You can look at the field in 3D. But I want to switch over probably to this one now, because time is running, and show you some of these other results here. Because really the main point was to look at the antenna parameters in the 3D in the 2x2 array. So you can see here that now all ports at phase 0. I have this kind of plot. So we have about 13.5 dB gain. Okay, and if I look at the plots, so that's case 1, which is all at 0. Then I have this kind of 3D pattern. Okay, with my gain is essentially oriented Z. If we do some phase shifting now, port 2. Phase 110, so this is far field phase 2, then I can see that it's starting to rotate a little bit, and then we go on and you can look at what different phasing will do to this antenna. Okay, and then here I actually did some cuts, and you can see the 2D cut of the radiation pattern. So we can say case 2 and 3, so those two of them are superposed here at 390. Or I can also look at phi equal 0 degrees for other. Okay, so we can see how this antenna behaves, how this array behaves. Okay, and you can see also this excitation we talked about at the beginning. So what's happening with ports 1 and 2 excited only? Okay, so you can see that. And by the way, so this is my electric field, and I'm exciting only port 1 and 2. 3 and 4 on the sides are not excited. If I excite both ports, and you can see all ports, and you can see what the electric field distribution looks like. So, and if all of them, so this is port 1 only excited. If you excite only 1, you can see what kind of field distribution you're gonna get, and consequently what happened with the radiation pattern. You can do the same thing with the magnetic field. Obviously, you can plot it, and you can look at this. And anytime you want to generate a plot, you can also go and do 3D. You can do iso clipping, section clipping. You can do vector plots. You can do streamlined plots. It's a whole bunch of different things. You can also look at a field data. You can probe the fields inside the structure, or you can do a linear cut through the geometry, see how the field varies within the geometry, and so on and so forth. So it's really allows you to you can explore your data quite nicely. And I noticed that I'm running out of time. So let me close by showing this last feature here, which is essentially if you want to do a report, document the data. I won't cover all these details, but we just say hit OK quickly and see that instead of doing this screen captures and so on, you can just have the whole process automated, and you'll capture all these figures and put them in a document. Then I chose the option to open it in Word. So this is actually my report inside SolidWorks. So this is my Word viewer, and I have my report inside here, and I can do the editing and all of that inside of SolidWorks. Okay. So basically, I can go to the introduction, or I can go to the results table. And if I scroll down, so I didn't write anything in the thing, but in the report generation phase. But you can see here, this is a document. It's a Word document from which you can obviously do the usual stuff. Word allows you to do if you want to format this, you want to crop this picture, and you do what comes naturally, and you can even zoom out and see the full page you want. Okay. So this gives you, I hope, a feel for what this what HFworks looks like. So I hope I showed you briefly these capabilities. And by the way, again, if you have questions, please.
Yes, Mr. Kabir, there is a question here on the chat. I wonder if you are able to see it or not. I can read it for you.
I'm not
so question number one is, what are we inferring from the output graphs of S parameter versus frequency? Also, for instance, S11 is the return loss. The greater the depth of true, it says between brackets in the graph, the better. So shall I repeat? What are we inferring from the output graphs of S parameters versus frequency? And S11 is the return loss, and it's saying the greater the depth of
so basically, of course, when from an antenna perspective, okay, matching is important for the gain of the antenna. Okay, so the deeper the S11, the smaller S11 in dBs. Okay, the more matching.
Are you showing anything right now?
No, I'm not showing.
Okay,
anything.
all right.
So the more the S11, the deeper the S11 dip is, the better match. So that's actually achieving. It's helping you with better performance, but at some point becomes marginal. So if you start getting to minus 20 dB, minus 30 dB, really the difference is minor in terms on the antenna gain. Okay, so. But yes, that's the level of matching that you are able to achieve, and matching means you're able to deliver more power to the antenna if you have more matching. So,
thank you for that.
Let me go back to screen sharing, and let me share the screen again. And let me see now if I can go back and wrap up this presentation. So I think we were at this point. We talked about this. So I showed you how we've done this inside, and I showed you some of these results, obviously. Okay, and this is basically a screenshot of the different radiation patterns that we are able to achieve and obtain with this 2x2 antenna. And you see on the upper right corner the actual fabricated device, and this measures track very, very closely with those measured results. So with that, I like to conclude this presentation. I think you've seen that you can achieve, good agreement with measurements. So simulation is accuracy and so on is there. So it's a reliable way to get your antenna designs done. It doesn't cost you prototyping and testing and all of that. So this design that we used as an example just shows you that there are many different ways you can do this millimeter wave stuff. So and the proposed design is one of them. So for the future development, as I mentioned, it's having the ability to simulate real world products and so on before committing to fabrication are going to be important if you want to innovate quickly and efficiently. And so I think HFworks is a good tool for that. And I hope that you're convinced that you've seen that HFworks has all you need to deal with antennas or any other 3D electromagnetic structures. And I hope that you've seen that inside SolidWorks, it's a very nicely, tightly integrated and a user-friendly workflow.
Well, thank you, Mr. Kabir. And now let me share with them a little bit of some resources. If you want to take, if they want to take some follow-up steps like getting your trials or asking for quotes or getting one-on-one demo, or if they have more technical, help that they need. And so I'll share with you what I have here. So just bear with me. So again, with us at HFworks Inc., whatever you need, be it a 2D, a 3D, a low frequency magnetic, electromagnetic, analysis, a transformer or motor or solenoid or RF antennas, waveguides, whatsoever, you can always have a solution with us and all inside SolidWorks. Some of the what in order for the the learning resources, what learning resources we provide out there. So first of all of our softwares come with what is called a demo viewer license, which comes for hundreds of predefined models for early users or new users that never used the software before. This will take by their hands, let them use these models and be able to check out different applications by simply clicking run and then plot the results, be able to dissect the results and look at everything, and that's one source. We do have on our website plenty of application notes on different applications that are done with HFworks, and they are available on our website, www.mmworks.com. We also publish every month a newsletter that covers what we have new in our products, and it has testimonies sometimes from customers and some benchmarking info and all of that is done by our customers, third party, that goes to tell about the ease of use, the accuracy of the results. We have a blog that where we publish also articles of interest related to HFworks. A customer can also purchase a training if wants upon buying a license. We also have a heavy presence in the social media on YouTube, LinkedIn, Twitter, Facebook, all of those social media. We have a heavy presence, so it's easy to find us. But to be more precise, you want to find us directly without going through this means. You can always go to our website right here, www.mmworks.com. Go to support, click on contact us, fill in the info, and that will come to us, and the right person will contact you. If it is technical, it will go to an application engineer. If it is a salesperson will get to you. So I do encourage you to take the next step of asking for trials, of thinking about adding this tool. It will add a lot of value to you, and we'll work with you. Of course, the best we can to present to you the best solution, both technically and commercially. Again, thanks a lot for attending and visit our website. That's really a pleasure to see you navigate it and click on different buttons to find more. But if you have particular questions, our email is available, sales@mmworks.com, and our phone number is available for all of you, and hopefully we'll get to hear back from you. Thank you everybody for taking the time to attend with us. You all have a great day or a great afternoon, whatever you are, or a great evening if you're a different time zone. We appreciate you, appreciate your attendance, and we hope to hear back from you. Bye-bye now.